But hopefully you guys have done the readings, right? We had 2 readings. One was hopefully basic. Was it basic? The Dennis and Misuna's paper. So. How about the other one? Was it difficult to read? Yeah. Yeah, that's. I warned you about it, but hopefully it'll become more clear when we go over the lecture today. Yeah, it's written from a different perspective, that's why it's a little bit hard to read, I think. But, okay, let's jump into the topic. Well, I guess you have 2 more data flow readings. Hopefully they're easier to read. This is more restricted data flow. And if you want to do more, I'll definitely give you more. But you can take a look at that. Last lecture, we covered a lot of interconnects, application-aware, Slack-driven packet scheduling, scalable topologies, and quality of service and topology co-design. Hopefully that was interesting to most of you. And that's an important part of the architecture. We'll switch to a very different topic today, which is data flow. And this has occupied computer architecture researchers for a long time. The paper you read, the first one was ISCA 1974, right? And people tried to build these data flow execution models at the ISA level for decades. And that wasn't successful, and we'll see the reasons why it wasn't successful. Although data flow at some other level has been successful, like programming model level. And people do data flow-based programming in many embedded systems today. Right? In fact, graphical programming models are usually based on data flow. But that's a different abstraction level. That's not the hardware-software interface layer. Hardware-software interface layer has been very difficult to change into a data flow model. Okay. Well, I guess I'll give you more readings. So. This is for your benefit, basically. But we'll cover some of them later on. I have introduced the concepts of data flow in 740 and 447, if you guys remember. But most of the models we've examined in these courses all assume that instructions are fetched and retired in sequential control flow order. Right? This is part of the von Neumann model of computation. In fact, it's a soul of the von Neumann model of computation. Right? It's a single program counter, sequential execution, and control flow determines the fetch order and the retirement order. In fact, well, even execution order, right? The strict von Neumann model is you don't start executing the next instruction until you complete the instruction that you're currently working on. Even pipelining breaks that model. But microarchitecturally it breaks the model. Architecturally, we still satisfy the model, right? What is exposed to the programmer is the von Neumann model. And out-of-order execution is similar. Right? At the architecture level, again, it obeys the control flow model or von Neumann model. But at the microarchitecture level, now you have a window of instructions that are executed in data flow order. And this is based on the principles that we will talk about today. Basically, what is data flow order? You execute instructions when the operands become available. I guess I should put this on. Now I remembered. Oh. Yeah, you execute an instruction when you even fetch an instruction when its operands become available. And the papers you read have done that. In fact, real machines have been built that have done that. Basically, in a data flow machine, a program consists of data flow nodes. And you all know what a data flow node is, right? It fires, meaning it's fetched and executed when all of its inputs are ready. In other words, when all of its inputs have tokens, incoming tokens. That's what means for a node to be ready. And we'll see what tokens are. So one example of a data flow node is this multiplication node. And you can represent this instruction like this. This is the operand, opcode. This is the argument 1, argument 2, and whether the tokens are present on the left argument and the right argument. And this is the destination node where the result should go to. If you think of this connected to another node here, that destination node has should have some address, right? We still need to store these nodes somewhere. So think you still have memory addresses associated with each instruction. But we don't have a program counter saying you're supposed to be executing this instruction at this point in time. That program counter doesn't exist because the node is fetched when its operands are ready. So let's take a look at the Dataflow nodes first. Well, you can imagine anything to be a Dataflow node, right? But some basic ones. This is a conditional node, right? Basically, you have a data input and a control input. And the control input determines which output the data input should take. So basically, this node fires when the data input has a token and the control input has a token. In this case, data input is X and control input says false. Basically, what happens is that in that case, this node fires and sends the input to the false output. Make sense? This way you can implement an if-else structure. You can do comparisons that evaluate to true outputs in this case, right? Basically, it's a greater than relational node. Is the X input greater than the Y input, or left input greater than the right input? Yeah, I should be consistent, left and right. Let's do it that way. And you generate a true token. Basically, this node fires again when both of its inputs are ready. When one of its inputs is ready, it doesn't fire. It just waits for the second input to arrive, right? And the second input may arrive at a different time because depending on what happens on this part of the Dataflow subgraph that leads to the left arc, right? There may be a lot of dependencies over there, or there may be long latency operations there. So this node fires when both of its inputs are ready. So this will translate into some machine structures that we will see. Somehow you need to keep track of the readiness of both inputs of a Dataflow node. Right? And once both inputs become ready, then you can execute the instruction, and the result is generated as an output token, which is true in this case. Another node, as I said, it could be arbitrarily complex, right? This is a barrier synchronization node, for example. You could implement it as a big Dataflow node. And you can have a large number of inputs. And basically, this node fires when all of the inputs have tokens. And it basically passes the tokens to the outputs. That's one way of implementing barrier synchronization. This way, your threads can continue to execute. Or some operations can continue to be done, depending on what comes afterwards, right? Okay. Basically, if you have this kind of nodes, you can add more. We'll take a look at more. But a small set of Dataflow operators can be used to define a general programming language. Right? You can think of this as your programming language. It's graphical, nice. You can reason about it. Right? This is a fork, for example. This is basically to implement fan-out. What if you have multiple destinations? You can have a fork node. It's not shown here. It's kind of implicit. But it's really a node, right? It generates fan-out. Why do you want to have this? Because you don't want to have arbitrary set of destinations, right? If an instruction has 1,000 destinations, you don't want to store the 1,000 destinations in one instruction. Instead, you can fork. You can have more instructions to fork. Well, I guess you could have a variable length ISA and have a bigger instruction for those 1,000 destination instructions, but that's another choice. Well, that's an addition here. This is a switch node. These are to implement branches again. We've seen this. And this is a merge node. Well, I guess we had seen the merge node. We hadn't seen the switch node. No, we had seen the merge node. We had seen the switch node, right? The switch node is the same as this one. But merge node is a select, basically, right? You select whether or not you pass the true input or the false input. Make sense? If the control input, again, well, I guess this is an interesting case, right? You can imagine you have a control input and you have two data inputs, and the idea is depending on the value of the control input, you pick one of the data inputs to pass as the output token. Now, in this case, you don't really need to wait for all of the operands, right, to fire this node, depending on the value that you have here. Does that make sense? Because if this is true and the true input has arrived, then you know what to take. But that may be complex to implement. So normally you would wait all of the inputs to arrive and then pass the appropriate input to the output. OK. So you can build Dataflow graphs. And this is one Dataflow graph that implements this function. I guess x equals a plus b, y equals b times 7. And then you have x minus y times x plus y. Right? This is x, this is y. This is x minus y, this is x plus y. And this is a multiplication of those values. And this is a very simple Dataflow graph. And values in these Dataflow graphs are represented as tokens. So what is a token, to be concrete? Basically, a token is this tuple. It specifies which instruction to fetch. It specifies which port to go to for that instruction, left input or right input. And it specifies a value. Right? So if you take a look at this particular arc, and arcs are supposed to contain tokens. In this case, this particular token has an instruction pointer of 3. So when this instruction executes, it generates a token. This particular token generates another token here. But let's take a look at this token. This token has a destination, IP3, port left. It goes into the left port of this instruction, and whatever value that's generated from that instruction. So basically, when you execute this instruction, from the instruction format, you get the destination IP and the destination port, and you append to that the value that's generated by the execution, and then send it to the destination. And somehow there is some logic that determines, that stores this token and figures out whether or not to actually execute this instruction, fetch and execute that instruction, because you do not know whether the right token is ready yet, which means that you may need to wait for the right token. Or if the right token is ready, somehow you need to figure that out and fetch the instruction. Make sense? So that will be the token matching logic that we will see. Yeah, basically an operator executes when all of its input tokens are present, and the copies of the result token are distributed to the destination operators, which are specified by the instruction. So you can see that there's no separate control flow here, right? If you have a branch, well, I guess this is the branchy part. You have seen this before in my classes, I think. This is an example Dataflow program. It's very simple. And you can probably say what it does. I guess in this case, n is a non-negative number. Is that true? That's right. I guess that's my question to you. What does this Dataflow program do? What is the value of the output? You can see the inputs, right? I cannot see it actually. This is supposed to be 1, and that's n. Anybody? Yes? So n factorial. Who agrees with Brian? Okay, many people. I guess that's true, right? It does n factorial. Anybody?
No.
Oh.
I didn't see one.
Got a different answer? Okay, yeah, you didn't see the 1? Yeah, that 1 is important, basically. So you can see that n is copied here, and this is a test. N is greater than 0, assuming that, let's assume that it's greater than 0. Then you copy that true or false value. This produces a true or false output. And that Boolean controls whether you send the output or whether you keep iterating around this loop, if you will. So let's say if this is true, then 1 is passed through this way. And we'll get the output of this. This node will fire when this output is ready. But let's assume that it's not ready now. I guess n is also copied here. And this is a branch node. And if this is true, then that n goes down this node fires. So basically, n is passed through this arc if this evaluates to true. And this evaluates to true if n is greater than 0, right? And then n gets copied here. So you have 1 here and n here. So 1 times n. And you also decrement n. So you get n minus 1 over here. So in the next iteration, you get n minus 1. So you have n here. I guess n iterates here. In the next iteration, you have n here, and then n minus 1 down here. You multiply n and n minus 1. And that result gets input here. In the next iteration, here you have n times n minus 1. Here you have n minus 2 because you've decremented. In the next iteration, you have n times n minus 1, n minus 2, dot, 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 right? So that's the factorial. And this works nicely. It may not be the most parallel way of implementing factorial, but it works, right? So you could imagine building an entire program this way. In fact, you could imagine, you could build any program using this Dataflow graph, although we'll see some challenges later. Any questions? So you've seen that Dataflow graph before. So this is one interesting comparison of control flow versus Dataflow from one of the readings. I think this is a Wien paper, Dataflow Machine Architecture, that I didn't assign. I think it's about 50 pages or so. It's a computing surveys paper. But it kind of nicely points out the differences, right? In a control flow program, you have the program memory and the data memory. And these arcs point to locations that are referenced or created. Whereas in Dataflow, this is your memory, and these arcs actually give you the communication, right? You don't have a separate memory here, although we will see that we will need that memory for other reasons, right? But for values that are communicated, those are basically your arcs. But now each instruction contains pointers. So here, the control flow is implicit, right? That's the sequential. You go from this instruction to this instruction to this instruction. Here, there is no control flow. Each instruction has pointers via the arcs to all instructions that consume its results. Okay, so now we have the concept of data flow. Now, how do you build a machine that can execute this model? Assume that this is your ISA. Well, the paper you read first is a static data flow machine. Basically, you have a node, and there can be only one instance of that node that's enabled for firing. That's what static means. You cannot have dynamic instances of the same node. And a data flow node is fired only when all of the tokens are available on its inputs arcs and no tokens exist on its output arcs. So, and there can be only one token on one arc. Right? So what does this look like? Basically, you can have a machine like this that stores the entire program. These are called instruction templates. And each arc in the graph has an operand slot in the program. So this is the same thing I showed you before. This is instruction 1. This is the opcode. This is the destination, 3 left. The resulting token should go to instruction at 3 left port. And also it should go to the instruction at 4 left port of that instruction. And these are the operands of this current instruction, instruction 1. And these present bits say whether a token is present for that operand. And if we, okay, I guess we don't simulate it here. But these present bits are set when both tokens are present. And this instruction can now execute. There's some logic that determines if both of them are present. And that instruction executes. When it executes, It basically appends its value to these destination identifiers, forms a token, and sends it across the sends it to the destination instruction. And you know the destination instruction, right? 3. Basically, when this instruction executes, you set the presence bit of instruction 3 left operand. You also set the presence bit of instruction 4 left operand. Right? So you know which presence bits to set exactly when this instruction executes. Does that make sense? So it's a little bit different from the out-of-order engine. Here you don't need to do a search because your program already specified what are your destinations. Right? OK. And there's only one presence bit. There's only one instance of the instruction that can execute. And this is basically the same picture, if you remember from that paper. I guess let's see if there's anything I need to emphasize here. Yeah, so I guess what happens if you're in a loop in a machine like this? Let's say this is your loop body, and you want to loop and execute it many times. You have one instance of the instruction, right, in the loop body. How can you do that? Well, you need to divide your program statically across such processors. That's the problem with the static Dataflow machine, because there's no way to have multiple instances of the same instruction. Does that make sense? I mean, these concepts are probably simple to you right now because there's no machine like this today, right? But you can put the different iterations to different processors, assuming there is no communication, of course. And you can have different processors like this. OK. So that's static data flow. I think I'll skip this picture. We can get back to this. So that's, of course, very limiting, right? You do want to be able to execute loops. And you want to somehow dynamically, instead of statically partitioning your programs, you want somehow this dynamic execution to happen naturally. Also, what happens with function calls, right? You always replicate the function, because you cannot have multiple instances of the same function executing at the same time with something like this, because you have only one instance of the instruction. Right? So that's very limiting. So to get full advantage of the data flow, what you really want is you want to be able to execute multiple instances of the same instruction. Now, what does this mean? This means that you want to be able to store multiple tokens per input. Right? If you think about this, I guess this is better. You have this Dataflow node, and I'm going to do this looping, if you will. You want to have one instance present, and it'll generate a token. And at the same time, you want to have other instances, maybe tokens of different colors, right, present, so that you get maximum parallelism, right? And you want to have another instance. And you want to have, I don't know, I'll run out of things. And this will be a problem in Dataflow also. But if you think of a loop iteration, that's what's happening, right? You have the same instruction that is being executed with different pairs of tokens. So to get the parallelism, you really need an unbounded queue in your inputs. But static Dataflow machine doesn't provide that, right? And there's another problem. Even if you have unbounded queues, let's say you were able to provide these queues at the input of an instruction, there's nothing that guarantees that these tokens that are supposed to be paired arrive at the same order. Right? It may be that because of variable latencies in execution, I'll call this the empty token is not a good word. I guess token from iteration 1. On the left side, token from iteration 1 arrives. And on the right side, token from iteration 2 arrives. You don't want to be executing this instruction with tokens from different iterations, right? makes no sense. So static data flow neither has the ability to have multiple tokens because it has a single instance of the instruction. And even if it did, there's no mechanism to actually match the tokens from different iterations. Match the tokens from the same iteration. So that's why it cannot support function calls or loops. It also cannot support data structures, but that's due to a different problem. Okay? So how do you support something like this? Well, I guess let's take a look at reentrancy. This is called Reentrant Code. Are you guys familiar with that term? You read that paper. So Reentrant Code means basically you re-enter the same code. That's simple. And function calls and loops are one example. I think I've kind of given you this, but if you look at this, if you can see this, this is from the paper you read. Maybe I'll write it over here too. This is basically S plus. I cannot even read it. I don't know how you can read it. Maybe it's easier to read from farther away, not from this close. But this is basically the code for this, S plus AI times BI. And let's assume that this is only one iteration, and then we'll think about the problems with multiple iterations. This is how the data flow graph for this will execute, right? First of all, or is it J? OK, this says J, and this says I. That's a bug in the paper. So I'll modify it to J. Somebody did not proofread this paper, I guess. OK, so this node basically fires when J appears, right? You get the AJ input here, and then BJ input here. And then you, can I read this? And then you multiply them, right? Once these two nodes fire, they generate an output token. And then this node fires, which is a multiplication node, which is this part. And then it generates an output token. And then this node now can fire because S was available. Now both of its inputs are available, which generates an output token. Now assume that this was in a loop or in a function, and the operations took variable time to execute, meaning things arrived at different orders. Right? Now how do you ensure that the tokens that match are of the same invocation? Basically, this selects maybe from different, right? This AJ, this may take a long while to fetch from memory, and we'll see that later on. This may take a short time. And for different iterations, you can have variable latencies. There's nothing that guarantees that the two inputs that come to this node are from the same iteration. So how do you guarantee that? Basically, that's the concept of tagging. Now you need to somehow be dynamic in your data flow. Basically have multiple instances of your instruction that are associated, and each instance is associated with a different iteration. That's the idea. In a dynamic data flow architecture, you allocate an instruction template or a frame, and people call it context also. I think in your in the paper it calls both context and frame. I don't remember very well. Was it context or a frame? No? You guys don't remember either? OK. Basically, the machine dynamically allocates a frame to support each loop iteration and procedure call. And we'll see that you need to somehow deallocate these frames also. You need a resource manager to actually manage this execution. Right? So when you're done with a loop iteration, somehow you need to get that out of the machine. When you're done with a function call, you need to get the frame out of the machine. And now your token is tagged with a frame pointer. And this frame pointer could be the iteration count. And it could be where the function was called from. Right? You need to handle these differently. Now the token is expanded. You cannot just have an instruction, but you need to have which instance of that instruction that this data belongs to. Make sense? It's simple. Okay, so what does a frame look like? This is one example of a frame. It doesn't have to be this way. But now your program is this. This is the same program that I showed you before, abbreviated a little bit. Remember, this is the add, and the destination is 3 left and 4 left. Now you have a frame pointer. And when you actually, let's say, when this add executes, okay, I'll do this. So for each iteration, you allocate a frame. And this frame stores the output of the add in this case. So for example, when this add executes, it generates a value at 3L, right? And that 3L happens to be 7 here. Let's take a look at actually a better example. This is the monsoon processor that actually exactly operates using the concept of this frame. Each token is tagged with the frame pointer. So let's assume that a token becomes available. It first goes through this code store, and it fetches the instruction that's specified by the token. And you know that the token specifies an IP, right? You fetch the instruction, and it doesn't need to be in this order. You could actually do it this order also, but that's okay. You fetch the instruction, and you also know the frame pointer, right? Once you fetch the instruction, you also know how many inputs it requires. Right? If it requires only one input, then you don't need to go here, because that's the token. The token that's generated says this is the input, this is the value, and this is the frame. Okay, this is kind of slow. Let's say one input is ready, but the other input is not ready. Then the next step is basically check whether the other input is ready. In this case, the other input is not ready because you, in the frame pointer and the instruction address, you do not find another token. So I guess to explain this a little bit better, we're talking about instruction 3, right? And let's say frame pointer is frame pointer 0. And instruction 3 IP is 3. And then port is left. And then value is, I don't know, 1,000 is produced. I guess we should really put 7 over there. But OK, I'll do 7. Let's say this token is this token. What happens is you first query the IP at 3. Figure out that this instruction needs multiple operands. And then you query frame pointer 0. Check if a token already exists there. A token already doesn't exist, which means that the other input has not been produced yet. So you store value 7 in that frame. Right. And now you need to wait for the other token to come, because only one token for that instruction is ready, which is the left token. And the other token comes, and it's supposed to be this, right? FP0, 3, right, I don't know. Now I can put 1,000. It queries that code, fetches the code, and then checks whether a token already exists, a matching token exists. This is the token matching process. How do you check whether the matching token exists? You take the frame pointer and index into that frame and get the operand associated with that particular instruction. Right? And the token already exists. So now what you can do is you can say, oh, I can execute this instruction, right? Because both tokens are ready. Or both data values are ready. Both operands are ready. So how do you execute that instruction? Now you form a packet, if you will, with the opcode of the instruction, because you've already fetched the instruction, the 2 data values, the frame pointer, and you already know the destinations. That's the token. That's the packet. and this is kind of a, we'll see this in a little bit more detail. But you have the packet of instruction, and you get the data, and you form 2 tokens afterwards, right? One goes to destination 1, one goes to destination 2. That's the idea. Okay? And ignore this. This could go to, I guess, yeah, you need to queue one of the tokens, right? If you have only one path. That, because you have 2 destinations, and one of them can be fetched right away, and the other one somehow you need to queue. Or otherwise you need to pipeline this stage also, right? Basically this is your pipeline register, but you could back up that pipeline register if you're generating a lot of tokens. Make sense? It's kind of like an out-of-order processor, but not really. So you fetch the instruction after the data is available. And you figure out whether the matching data, matching token, is also available. And if it's available, then you can now execute the instruction. You could do it the other way around also, right? You could actually do the operand fetch first and then the instruction fetch next. You really didn't need to do the instruction fetch here. But I'll let you think about the trade-offs. In the later slides, I'll show you do the operand fetch first. But you can think about the trade-offs associated. There have been machines built in both ways. OK. Any questions on this so far? This is the very basics. You can see the downsides and upsides, right? I guess just to look at the downsides and upsides quickly. First of all, I think one interesting thing here is you don't really need to store multiple operands for an instruction, right? You can store only one operand, assuming at most the most number of operands you have is 2. Because when the next one comes, you're going to match in the frames and you're going to execute it. And you can have many frames. Well, that's going to be a downside also. That's been one of the issues with Dataflow processors. How do you you can have a lot of instructions waiting for its matching operands. How do you control that parallelism? One other issue that we will get to is, what if you have back-to-back dependent instructions? It's not very efficient for that, right? You need to fetch the instruction, you need to fetch the operands, you need to do all of these overhead operations. It's hard to pipeline them. But we'll get to that. OK. OK, so we've talked about the concept of frame pointer. Now the question is, how do you actually generate these frame pointers? Right. This is also called context. And I think this figure shows the context. This is an example of a function call. I guess this is, how do you handle function calls, basically? I guess if you have a function call, I'm not going to use the Dataflow language here, but I guess I'll do this. Maybe call. And then you execute some code here, and then you need to return, right? And there may be some other parts of the program that want to execute this code at the same time, right? You need to have really different colors or different context IDs, because you want to be able to support multiple invocations of the same function at the same time. Right? Otherwise, you somehow need to prohibit some other part of the Dataflow graph from executing this code. And that kind of gets rid of the appeal of that function calls, right? You cannot share the code between different parts of the Dataflow graph. So how do you do that? Basically, you need to associate a context ID with each caller. And when the return value comes back, you need to ensure that that context ID is preserved, right? So when you call this function from this caller, the result should have the same context ID. That's the idea. And if this function is simultaneously called from some other caller, you have a context ID that's different from this context ID, maybe context ID 1. And the result is returned with context ID 1. So each token is tagged with that context ID. But somehow needs to manage, somebody needs to manage the allocation of these context IDs. Well, how is that done? The only thing you can do is do this in the Dataflow graph, right? Which means that before you go into this function, you have to somehow have nodes that change the context ID, that assign the context ID. So let's take a look at that. Basically, this is the caller. There are some nodes that extract the tag of the caller. And I guess I'll animate this. This is the caller. And these are the inputs to the function, let's say A1 through AN. And when the caller executes, you get the frame ID or the context ID. And then basically, you go into this Dataflow graph for function call. And at the end, you tag, you use this frame ID and use that to tag the outputs so that you get the you associate the right result with the call site. Make sense? You can think about this a little bit. So it's like a standard call return, except you need this to ensure that caller and the callee can be active at the same time, right? That's the interesting thing about Dataflow. You can have all of this active. There could be nodes that are here that are waiting for the tokens coming out of this function call, waiting for execution. Okay. Basically, what we've done is you need an extra mechanism to direct the output token of the function to the calling site, to the proper calling site. And this is done by sending special token containing the return node address. I think one other example, I'll show you this function call. Well, I guess, yeah, you can think of it this way, right? You have this parameter. It gets input into this procedure. And what happens is this procedure needs to take the address of the destination also, right? So you need a node that takes the result, and that also takes the address of the destination. This is the return point in the program, if you will. So this is the entry point into the function. You have a separate node that conveys the address of this return point, and that address of the return point is input to this node here, or set of nodes, which take the result and send the destination, send the result to the appropriate address, to the instruction with the appropriate address. Make sense? You could think of this as this is the return address, and the result, the data, needs to go to the return address, which means that you need to use this return address as part of your tag somehow. Right? You need to convey that to the node that communicates the result back to the function. Is that clear? Maybe for some of you. Those of you who are not sleeping, at least. Okay. Okay. It's nothing magic. It's simple. You can do all of these with Dataflow operations. Similarly, with the function calls, you can read this also. But with a function call, this is an example of a function call. It's more complicated than it needs to be, but you can look at this. Initially, x and y are set to 0. While x is less than 10, x is incremented, and y is incremented with the return value of hx. Well, so this is a loop, actually. Did I say function call? Basically, each iteration needs to receive a new tag. Right? How do you do that? Well, you, again, augment the Dataflow graph such that you allocate a new tag when you get to the next iteration. So there's some, this is initial. 0, you allocate a tag, you get the x and y. And here you check whether x is less than 10. Assume that it's less than 10. Then you enable the next tag, right? And you generate a next tag. These are the inputs to the next iteration, so that you ensure that the next iteration instructions receive tokens with the same tag, right? And then you keep generating new tags as you iterate over the iterations. Okay? There you go. Tokens belonging to consecutive iterations receive consecutive tags within this area, which is here. And then you can restore the tag at the very end. Okay. To generate the new x and new y that you need at the end. Okay? I think your paper covered a lot of this. So one issue with these machines is many loop iterations can be present at the same time. Right? Yeah, think about 100,000 iterations in a loop, and which could happen. And you have only 256 processing elements. And this could swamp the machine, because you're not controlling any of this parallelism. You could have everything is happening based on data flow order. In control flow processors, the control flow is really controlling how many instructions are in the machine, right? You can easily stop at any time. Whereas here, which instructions you are able to execute, or which instructions are actually in the machine currently, are determined by which data has become available. And that has really nothing to do with control flow. It's based on data availability. Your data may be available because it's in your caches, right? And it may turn out that you have lots of instructions from many different iterations, and none of them are complete. Right? And what happens in that case? In that case, you need to store all of those tokens that are generated in these token matching units, or that frames, or those frames that we've seen. Which means that you need to have enough bits to represent the frame ID, first of all. But also, you need to have enough storage for that. So how do you solve that problem? One way is, of course, building an infinitely large machine, right? Which is, of course, not practical. Well, the solution is, yeah, you have a solution. That's right. Yeah, you can throttle, right? Instead of, because it's all data flow graph, right? In the data flow graph, you can actually control how many loops can be present in the machine. You can have a node saying, if there are 100 iterations that are currently active, then don't send the next token. Wait. Don't start the next iteration, right? And that's the idea. Throttle the loops. Control how many loop iterations can be in the machine at the same time. And that's what I said, basically. You need to have some changes to the data flow graph to inhibit token generation if the number of iterations is greater than n. Basically, it's a dynamic check. How many iterations are already in the machine? And when an iteration starts execution, you increment that. When an iteration finishes execution, you decrement that, and you compare that to some value. And that value can be dynamically determined by some other data flow graph node based on resource availability. Right? Now, you need to think from the data flow perspective. Right? Basically, some other node, let's call it the operating system or system software, looks at, with the data flow graph, looks at the availability of how many processors you have, and based on that, changes the input to that throttler and determines n. And there's another whole data flow graph doing that. Basically, your whole execution is a data flow graph. Your whole machine is a data flow graph. And it's all connected. And this is how the resource manager interacts with the program itself. It's a lot of fun, right? You don't have separate programs, if you will. Everything is communicating based on data. I guess separate programs are essentially disconnected data flow, but system software communicates, taps into those programs. And we'll see that resource manager. It's very appealing. It's beautiful, in fact. This is one of the things that are beautiful. OK. Well, this is the non-beautiful side, perhaps. Data structures. So by nature, this has write-once semantics, right? You may need to think about this a little bit. But each arc or token represents a data value. And an arc or token gets transformed by a Dataflow node into a new arc, new token, which means that there is no persistent state, at least the way we described a Dataflow graph. And that's where the beauty comes from. But you want persistent state. Right? Data structures, as we know them today, in imperative languages, are structures with persistent state. Right? You want to store an array and change the value. You want to store a linked list and change the value there. Well, how do you do that? Well, why do we want persistent state? Because it's just a natural representation for many things, right? Arrays. And arrays are actually easier to handle, but things like bank accounts and databases, right? You want to store lots of data, and you want to query, and you want to change it. I guess how do you ensure that? How do you get rid of this write-once semantics? And that has been part of the problem with Dataflow. And also, there's another reason you want persistent state, so that you can exploit locality, right? If every time you're generating a new value, you need to store it somewhere, you're not really exploiting locality. And where does it get stored? It gets stored in that frame storage, right? In that tag matching area. If you don't have, if a memory location, if the only thing you do is to read and update that memory location many times, in a Dataflow machine, it will be stored in many places in the same frame storage. Right? Whereas if you have like memory, then you can exploit locality. You don't need to replicate that. Does that make sense? It's kind of a similar problem in an out-of-order machine. You rename registers, right? And they get replicated instead of stored in one location. OK. So, well, of course, this is not feasible. You need to have some way of representing arrays or these other things. Basically, people have added data structures in Dataflow. And they reside in a structure store, which is really structure memory. And now tokens can carry pointers referring to these memory locations. Right? Now we have a load and store instruction that can load from and store to these locations. But now we'll see another problem, because it's still write-once semantics. We'll see why this is needed later on, I think, actually very quickly. But basically, this is what happens. This is a load instruction. It gets the input address, A, and returns a value. And this is a store instruction. It gets the input address, A, in the structure store. And it also has a value. This is the store node, I should say. And this is the fetch node or load node. And this fires when the address and value are both available. And the semantics is that it stores. Now, what does it mean to store? You have write-once semantics. But you can read multiple times. Right? So a memory location can go through these operations. Allocate the memory location. A resource manager does that. Write to it, and read many times from it, and deallocate. And there's no problem if a reader arrives before the writer at the memory location, because we're going to use the concept of full empty bits. If a location is not produced yet, the value is not produced yet, then the reader just waits for the store. And that's the idea of I structures. You have these, for each memory location, you have presence bits. It could be present, full, absent. I guess in this case, waiting is the empty. Absent means not allocated in this case, if I remember correctly. People use different terms. But think about it as full empty. Ignore the allocated state for now. In this case, there may be locations that are present or full that contain the data. And if a read comes there, the memory just returns the data. There may be locations that are waiting, which are empty. In that case, I guess waiting in this case means there are instructions that are waiting for it. There may be locations that are absent, which are empty. In that case, if a read comes to that location, it queues in that location. Basically inserts itself into a queue and waits. We'll see this with an example more clearly. But this example shows an execution sequence. Let's say you get an instruction or data flow node that attempts to read m+2 for instruction x. And instruction x gets queued in this deferred read request queue. And you could organize it in different ways, but basically you have a pointer from location m+2 that's currently empty, that has somebody waiting on it, that has a pointer to this deferred queue request, which says instruction x is waiting for this. And let's assume somebody writes to m+m in that afterwards, then this bit is set to present or full, and the data is written. Let's say later some instruction z reads from location m+3, which is absent at that point. This location turns into waiting, and the instruction gets added with a pointer to a deferred queue request with its tag. And then let's say somebody else writes to n, which sets the present bit and the data value. Let's say somebody else wants to read from m+2 after that. This read for instruction y will find that this location is in waiting state. It'll follow the pointer. X is waiting for that location. And then it'll add itself to that linked list. Right. Now, multiple instructions can be waiting for the same location. Basically, this is how you implement very fine-grained waiting, very fine-grained synchronization, if you will. So if you have a lock, you could be waiting for, this could be the lock address, and different instructions can be queued up and waiting for the lock. Make sense? OK. And then when the store, I guess this didn't complete the picture, when a store comes, let's say it stores to m+2 and a data value. What happens? That store checks the state. Oh, somebody's waiting. First of all, it sets the state to present, writes the data here, and wakes up this instruction and generates a token with the instructions tag and the value that was produced and sends it back. Right. Now, that instruction that's loading can wake up and continue execution. We'll see another example of this. OK? OK, I think this is something I'll leave you with, because this is the tough part. So this is nice for write once data structure, right? Now the question is, what if you want to write multiple times to the same location? And you want to also read multiple times. How do you order those requests? Now this becomes difficult, right? Because you have this Dataflow graph, and these writes and reads, there's no ordering at all in your Dataflow graph. There's no control flow ordering. There's no ordering that specifies how these should execute. And you need to stretch your mind and maybe find solutions to this problem. Yeah, how can you support them in a Dataflow machine? Can you implement a linked list? Or how can you implement a linked list? This is perhaps a more difficult problem than multi-threaded programming, right? In multi-threaded programming, somehow you have threads, and they're modifying the same data structure, and you somehow need to synchronize between them. Now, you don't even have threads. All you have is data-driven execution. So what are the ordering semantics for writes and reads? Well, in the way we described it, there is no ordering semantics. These just happen. But you want ordering semantics for some things, right? For example, if you want to have transactional execution, how do you guarantee that in a Dataflow machine? It's tough. It's not that easy. So I think if you think about the programming model, Dataflow doesn't fit well with the imperative programming model, where you have mutable state. We're very used to mutable state, right? Unless you're a guru in functional programming. We're very used to data structures where you can write multiple times. That becomes tough with Dataflow because you cannot really mutate the state easily. Okay, I'll let you think about this. This slide is for your benefit, for thinking, really. I don't think I'll have good answers. I don't think any of the Dataflow research had good answers. And this is where it became tough, because people have focused on the machine implementation, but didn't focus on the higher level. How do you actually bridge the gap between the software and the machine itself? And usually, whenever you design a new paradigm, that's the tough part. How can you get the software working with that underlying ISA? Or underlying even the language model here, right? It's very hard to expect all programmers to think about these functional languages and all programs to behave that way, like with write-once semantics. And if you talk to Arvind, he will tell you that also. He had an ISCA 2005 keynote. Some of the slides over here are from Arvind's ISCA keynote, and he was one of the big proponents of Dataflow. And he said what we did wrong was not to focus on software. And if there was some way of providing that layer such that the software could be easily transformed into something like this, which is hard, I think, then Dataflow could have been potentially successful. I think similar lessons actually have been seen recently also, right? I guess my favorite example is Intel's Larrabee. Intel's Larrabee had a very different execution model for graphics processors. And they focused a lot on the hardware implementation. But the software stack was lagging behind. It was very difficult to move that graphics software stack to a fully programmable array of x86 cores. I think that's an easier problem than this Dataflow problem, by the way. But that software is very important. When you're changing the model, if you do not provide a way of moving the software to that model, then you're essentially ignoring the big world. OK. So let's take a look at the MIT tag token Dataflow architecture a little bit. You read the paper. So I think this will be more of putting together all the concepts. And I'll end the lecture early today. But this is what a Dataflow machine actually looks like, putting it all together. You have these processor nodes. And you have the memory nodes that contain the data structures. And processor nodes contain the local program and stack memory. And you have these resource manager nodes. And everything is a Dataflow graph. Resource manager nodes, what do? They basically allocate context and frame identifiers, heaps, throttle loops, as we've discussed. And this is what the tag token architecture looks like. You have this weight match unit. It tries to match the incoming token and context ID to a waiting token with the same instruction address. And you can see that these are ordered differently from the monsoon architecture that we looked at briefly earlier. Basically, a token comes. You check whether an instruction with the same address with the same context ID has a waiting token that matches that token. Right? And if it does, now you can, and if those are the only tokens that this instruction is waiting for, then you can fetch the instruction from program memory and form a packet and execute the operation and form destination tokens. So if you look at the execution of one thing, I think we don't need to necessarily go through this. You can look at it yourself. But I guess I'll go through this very briefly just to show the operation of memory later on. These are the operations. These are destinations of the operations. And this is the memory location of each instruction. So you have the opcode and the destinations. And you have some context ID associated with the operation and the value. And this is the destination instruction address. This is the token, basically. So the token is a packet that contains the destination instruction address, left or right port, and the value, and the context ID. Here, somehow, they left out the context ID. So let's say you get the token. This token is produced 120R with context ID C. This is the value. This token first goes to this weight and match unit and checks basically what operation is done. You basically look up memory location 120. And that's an associative search, right? Because you don't want to have the entire memory here. You want to have an associative search that checks for 120. And then if 120 is present, the hope is that it's the left operand. Otherwise, something is wrong. You check the context ID. So it's an associative search on the instruction address, destination instruction address, as well as the context ID. And if something is present, that means that the corresponding token is already there, and you get the data value associated with that token, and append it to this token. Let's call it a packet now. You have instruction 120 to be fetched with context ID and with these two operands. Now you access program memory. Now this is the full memory. Now you can go and index memory location 120. And memory location 120 tells you that there's an add, and these are the destination operands. So now you form a packet. These are the destinations, context, add, operands, and now you execute the operation. That's the execute stage. And after executing the operation, then new tokens can be formed. This is the result. And you generate two tokens because you have two destinations. One token goes to 141, destination address 141, same context, result. The second token goes to destination 159 left, same context, and the result. So the difficulty is really here. software to work with this model, right? It's very hard to program these machines because debugging is difficult, right? How do you get a precise state in a Dataflow machine? Can you guys solve that problem? Programmer cannot reason about the state because there is no abstraction in the Dataflow machine. In the control flow machine, the abstraction is very, very simple. Programmer can reason where they are in the program exactly, right? It's this instruction. Von Neumann model is beautiful in that sense. It's beautiful for the programmer. The programmer knows the state at any point in time, or what should the state be at any point in time. They can reason about this. In a Dataflow machine, the machine is beautiful to do this, but the machine is not beautiful for the programmer because now the programmer has no idea which instructions are executed or which instructions are supposed to be executed, right? You could be anywhere depending on the latencies in your program. You could be in the middle of, you could take a cut at any point in your Dataflow graph. It's impossible for the programmer to reason about this. So debugging is very difficult. Other things are also difficult, interrupt and exception handling. Basically anything related to precise state. Anything that's easy with precise state is difficult with Dataflow engines because you don't have that precise state. Or you don't have a known precise state. At any point you can have a precise state, which is a cut across your Dataflow graph, but that's not known necessarily. That cannot be reasoned about. So this is perhaps the most difficult part in Dataflow. And that has made the ISA level Dataflow not successful. I mean, arguably, this is the reason. Because once you expose this to the ISA level, some programmer needs to reason about it. And even if it is just the system programmer or the compiler writer, it's very tough, right? OK. The other difficult reason that affects software significantly is dynamic data structure, right? In pure Dataflow models, it's hard to do this because you're writing multiple times to a memory location. How do you do that? I'll let you think about that. People have proposed different ways. I should have reordered these things. So ordering is software issues first. Too much parallelism is software plus hardware issue. High bookkeeping overhead is an implementation issue. There's another issue, which is instruction cycle is inefficient. What's an instruction cycle? You have an instruction processing that you need to do. You have a significant delay between dependent instructions. You cannot execute them back to back very quickly. And you don't exploit locality also, right? Always you generate a new packet. You move data. So if you think about it, the concept of register file doesn't exist in Dataflow, right? And register file is one of the very fundamental things in a control for a processor that executes locality. Right? It's the highest level of the memory hierarchy or lowest level of the memory hierarchy. Right? So because you don't have that locality that's exploited, you keep generating these new tokens. And that makes the machine inefficient. So we'll see some models later on in the next lecture that try to solve this problem. So one way of solving this problem is actually do what is called a macro data flow. So you can do data flow at block granularities. So you can think of this block. And this block can be executed in a control flow-like processor. So your core can be control flow-like, but these, and then you can have another block maybe, and then you can have another block. These blocks are executed in a control flow manner, so you can have registers in between, and maybe you can have simple sequencing. But across the blocks, you have data flow. So it's a hybrid model right now, and your machine needs to support this. But once you have this model, this can be executed very efficiently. You can exploit register locality here. Right? You can even divide your data flow graph such that you can exploit that locality well. And we'll see this in the next lecture, I think. Oh, I guess I'll finish this. Yeah. Yeah, I guess I'll stop here after I finish this. So can we get the best of both worlds? So obviously, Dataflow has advantages, irregular parallelism, but a lot of disadvantages also. So people have tried to get the best of both worlds whenever you have something like this, right? And there are two possibilities. Well, I should say at least two. One model which has been very, very successful so far, and you'll read the papers about this, is you keep control flow at the ISA level and do data flow underneath. Of course, you cannot do full data flow. That's why it's called a restricted data flow, right? Because if you keep control flow, you get the inefficiencies of the control flow also, which is sequencing through the code. That's inefficient. But you can sequence through maybe a window of the code and do data flow within that window. This preserves sequential semantics, makes programmers' life much, much easier. But also gets some of the benefits of data flow without the downsides. The second model, which has not been as successful because it's, again, it doesn't preserve the sequential semantics, or it doesn't preserve the nice properties that control flow has, which is easy debugging, dynamic data structures, ... is this model that I told you. Keep the data flow model, but incorporate control flow at the ISA level to improve efficiency, exploit locality, and ease resource management. That's this macro data flow. Or another way of thinking about it is you can incorporate threads into data flow. Right? Basically, what is control flow? It's essentially a thread. It's a statically ordered instructions. And when the first instruction is fired, remaining instructions execute without interruption. And how do you do that? You could have a control flow-based processor to do that. Now, this gets some of the benefits of control flow, but maybe potentially not the most important benefits, which is debugging. Right? Again, how do you debug this processor? Now, you coarsen the granularity where perhaps interrupts can happen, but you still didn't provide any reasoning to the programmer, which blocks are done currently. That reasoning doesn't exist. So that's why this Model 2 has not been successful. But we'll cover this briefly in the next lecture. But hopefully you'll enjoy the papers on Model 1. I did not assign a paper on Model 2, but I'll cover this. Any questions?
So Model 1 is out of order.
That's right, yes.
And Model 2 is like pipeline software development.
Model 2 processors don't exist today. Model 1 is, yes, this is whatever you see in Intel, AMD, or any kind of high-performance processor today. Model 2 is basically this. You have data flow at a block granularity. Okay. Any questions? This is a fascinating topic to think about. It does stretch your thinking a little bit, especially if you're so used to the control flow paradigm. But it's also fun to think about these things. Because who knows, maybe you'll come up with a new paradigm that combines them in a different way. But if you come up with a new paradigm, never ever forget what's up there, which is the programmer. Right? If you make life harder for the programmer, then your model is not going to be useful. If you make life impossible for the programmer, which I would argue that some of these data flow machines did, then you can guarantee that your model is not going to be useful. Because you're building hardware not for the beauty of the hardware, not for the beauty of processing, not for getting high parallelism. It's really, if you cannot support that software stack on top of you, it doesn't matter how much parallelism you extract, right? Okay, I guess we'll continue on Friday.